So I'm back at the Origins 2026 conference here at the Sorbonne in Paris with Nader Haghighipour. Is that correct?
That's right.
From a planetary scientist, a very well respected planetary scientist at the University of Hawaii in Manoa. You came a long way for this conference.
Yes, I did.
Nadir. And you gave a fascinating talk earlier. I think it was the day before yesterday, on 1,000 simulations that you did in Hawaii using a random starting point for our own solar system. Or am I hearing you wrong?
Yeah, that's correct. Yes.
So tell me the major findings that you came away with.
So we find a few major things that solves some of the biggest outstanding problems in planetary formation, especially in the formation of terrestrial planets. We find that formation of Earth is organic, is a natural outcome of the evolution of the system. We find that Venus appears in about 28% of the times and maintains its orbit, sometimes in the habitable zone of the stars, sometimes slightly outside. But more importantly, we figured out that the problem, the longest standing problem with the big mass of Mars no longer exists. And the approach that we have taken basically solves that problem. Mars appears quite a number of times, and it appears as an object being small in the vicinity of the current orbit of Mars. And also it gives us a good handle on the way that objects, especially protoplanets, transport water to Earth and the delivery of water and the internal composition of Earth. It's a good starting point to more complex simulations where we're going to resolve the big collisions and hopefully be able to explain the radioisotopes and the distribution of material inside Earth and its geological properties.
And you told the title of your paper in part was Back to First Principles.
That is correct.
And then what do you mean by that?
So for many years, for almost 3 decades, we have been doing simulations with the specific initial conditions that were chosen for the mere purpose of easing computational simulations and computational tools. But now what we are doing is that we have reached to a point that those initial conditions have given us all that they could. We have figured out all the underlying physics that could come out of it. And now we are at the stage that we can go back to the basic principles and start from the beginning and make the simulations quantifiable. That's the point, to make the simulations comparable with geological data, with atmospheric data and properties of Earth. We have to start from the beginning. And this time, that whole thing about first principle is that we no longer choose initial conditions by hand that will ease the computations. We start from what it could be, and we let the physics carry us.
And what's different, you've been doing this for at least 25 years, these type simulations, correct?
Right, that's correct, yeah.
And I just asked you, I said, how has computational power or AI or machine learning, whatever, how has it affected your ability to run such simulations? In this paper, you said you ran 1,000 simulations. So speak to that. I mean, what you told me in the interview just now was incredible. That's about how our computational ability has made these accessible and easier to do, correct?
Sure, right, that's correct. So when we started doing this type of simulations 25, 30 years ago, our computational tools were so limited and were not strong enough to handle the interactions between many bodies. So we had to choose small specific objects, and we had to put them in specific places so the simulations would actually carry out, and they wouldn't carry out for so many months or years. They would be actually practical to carry that. But now that the computers are so advanced that instead of a couple of hundred, we can do several thousand objects. So we take a disk of protoplanetary bodies that consist of several thousand bodies, and then we integrate all of them, and we simulate the interaction with one another. And as opposed to the past, that the simulations would take months, sometimes 6 to 8 months to run. Now we run those simulations within 4, 6 to 8 weeks.
And
And
once you have, you used to have to use supercomputers for this type of
right,
work,
right.
and nowadays you basically can do it on a powerful laptop or something.
Absolutely, yes. And if your laptop is powerful, you can actually do these type of simulations on it. I normally use it on computers that have been designed for this purpose. But yes, current laptops do have the ability to run these simulations.
And you can actually tweak your simulations much more easily than before.
That's absolutely correct.
And
Yes.
so, just to finish up, you were telling me something that is quite amazing, and that is that because of the stochasticity,
Right.
I don't know if I'm pronouncing that
Oh yeah,
correctly,
you said right. Yes.
of these models, that even a small variation in initial conditions can have a great impact on the final product of a
Right.
given solar system,
Right.
or even our solar system.
Right.
And I said, do you think that our Earth is an anomaly? And you said a resounding no.
Right.
And then tell us what you were telling me in the interview about how Earth could have taken several different pathways to life as we know it.
Right. So we don't know how life started on Earth, and we don't know. But what we know is that as it started, it took different variety of different paths and bifurcations. Many of those paths and the bifurcations they ceased. But somehow one of them went to the next step, and again a lot of bifurcations, and one of them went to the next step, and somehow life on Earth managed to find its way to become to maintain itself and become sustainable. But that does not, what I mentioned in the interview was that does not mean the path to the current state of life on Earth is unique, and the way that Earth went through it is the only way. Depending on the characteristic of the planet, depending on the environment where the planet is, how big or small it is, and its internal composition, its atmospheric composition, the life, no matter how it starts, still goes through different bifurcations, but different pathways, different bifurcations will get you to the current state of Earth. And that's why I said that there is no reason to believe that our Earth is a fluke, or the pathway that life went through it is the unique way, and we can't find Earth life other planets. As a matter of fact, that bifurcations, the stochasticity in the life to find this path to get to what it is guarantees that our Earth is not unique.
And so, in other words, you think that we're not going to find life exactly like Earth on an exo-Earth. I mean, that would just be an incredible fluke. But there's probably going to be life, probably advanced life, but the pathway to that advanced life
may be different from ours.
may be very different from ours.
Yeah.
Okay. So thank you so much,
Absolutely.
Nader, for your time today. I appreciate it.
Sure.
Enjoy your time in Paris.
Thank you very much.